So, welcome everyone to today's video on some question and answers on the topic of circular motion. So, we have discussed centripetal forces. What are centripetal forces? They are some real forces like gravitational force, tension force, which act on bodies and act as centripetal forces and keep them going in curvilinear motion or circular motion. In the same way, we have discussed what are centrifugal forces. Centrifugal forces are forces which act on a body when you observe that body from some rotating frame of reference. So they are applied in radially outward direction. Just like centripetal force is required in radially inward direction. So let us start with a question. We start with some relatively easy question and then move on with the difficulty. So the first question is that of a train. So we have a train. It's going with the speed of 54 kilometers per hour. It's going with some speed of 54 kilometers per hour in a radius of 30 meters. So it's going in a circular track of radius 30 meters, and this is the speed given of that train. So just like we analyze the case of a car, that a car can go with a particular speed without much wear and tear to its tires, and for that we neglect the friction acting on the car. We try to do away with the friction on the car. In the same way, this question also asks us that there is a train which is going with the speed of 54 kilometers per hour with on a circular track of radius 30 meters. So we have to provide banking to the tracks so that the train, whose mass is 10 power 6 kg, is able to go without much hassle on the curve. So that is the language of the question. What is the angle of banking required to prevent veering out of the rail? So the mass of the train is also given. So we already know that for a car, what is the speed required to keep it at the angle of banking? So the expression is V is equal to Rg tan theta. V square is equal to Rg tan theta. So from this we can find the value of tan theta. Tan theta would be V square divided by Rg. So tan theta could come out to be, now this velocity can be converted into meters per second, so that would be some 15 meters per second. So that would come out to be some 225 meters square per second square. Radius of track 30 meters, and action of gravity some 9.8 meter per second square. So we have substituted the value of the speed of the car, that is speed of the train, that is 15 meter per second, the radius of the circular track, that is 30, and the action of gravity, which is given as 9.8 meter per second square. So what would be the value of tan theta so that the train is able to go properly on the track? So the value of tan theta comes out to be some particular value, and from that we can find the value of theta by taking tan inverse of this whole ratio. So this angle comes out to be some 37.8 degrees, something like that, 37 degrees and so on. So this is a purely mathematical calculation, but the important part of this question is that even though we are considering a train, it is not a really different case when we are talking about a car which is going on a circular track, and the mass of the train is not relevant in this case. So this is a question taken from NCERT. So let us move on to the next one. So the next question, we are considering that of a string. So in the previous video we considered a string which was connected to a bob, and the bob was going in some horizontal circular motion, and the string itself was describing a cone. So now we are connecting the same bob to two strings. So what would happen now? We have two strings. which are having the same length as that of the distance between these two vertices. So the distance between this point and this point is L. Length of the string is also L, and this length is also L. So this complete circular arc which the string is, which the particle describes, that particular arc is having some radius, right? So now let's say the mass of the bob is some m, and there is some actual gravity g, and the question which we considered was we had only one string, right? Now we are having two strings. That is the only difference now. So we are given some angular velocity with which this whole system is going in a circle, and both the strings are describing some cones. So let's name the strings. The string which is the upper string is named AB, and the string which is below is named some BC. So we know the lengths AB and BC are equal, and they themselves are equal to L. Let's say the tension in string number 1 is some T1. This would be like this, something like this, acting on this mass M, and the tension on string number 2 would be something like this, T2. So the first part of the question is A part, find T1 and T2. This is part A. And part B of the question is find the minimum value of omega so that the tensions do not become zero. That is, the strings do not slack. So what would be the minimum value of omega for which the strings would keep going in a circle? How would you find that? So let's say it is going in some radius of circle r, which we can easily find. Let us name it r only. So what are the forces acting on the mass m? First we will be evaluating T1 and T2. The more forces acting on mass m would be the gravitation force mg, tension T2 along the string, and tension T1 along the string, and the centrifugal force in outward direction. So let us now apply the concept of centrifugal force in this particular area, and let us see how it helps us in solving some question. So it is m omega square r. Its value is radially outward. So since all the lengths in the string are same, let's say this angle is some theta, this angle is some theta. So we know angle theta is 30 degree. So let us start drawing the equation. So let us try to break the components of T1 and T2 in the vertical direction first. So in the vertical direction, your tension T1, that is acting in AB direction, that would be upward direction, and the same with T2 is acting in downward direction. So it is opposite to it, and the components would be the sine component, sine theta. So why the sine theta component? Because it is in front of angle theta, this component, so T1 sine theta. Similar T2 sine theta is opposite to that, so that is a negative sign. Again mg is in downward direction, so this would come out to be equal to mg. That is, the difference of tensions, sine theta component balances the gravitational force acting on the ball of mass m. And in the same way, I can write the T1 and T2 cos components. So T1 plus T2 cos theta. So again, let me explain how this comes. So T1 cos theta is this component of tension 1, and similarly T2 cos theta would be another component. So I had already taken the common component cos theta. So this can be written as T1 plus T2 some cos theta, and that would be equal to the centrifugal force in radially outward direction, which is the opposite direction. So first we want to find the values of T1 and T2, so those should be relatively easy to find. We have to simply take the value of sine theta cos theta over there and add these two values to evaluate. So value of sine theta and cos theta we already know. The value of sine theta is half, because sine 30 degree is equal to half. So we can substitute half in place of sine 30 that we have already established, and cos 30 degree would be some root 3 upon 2. So this was going to give us the equation that T1 minus T2 is equal to 2 mg and T1 plus T2 is equal to 2 by root 3 m omega square r, or whatever the value of r is, we can substitute that. So after adding T1 and T2, we would get the value of T1 would be mg plus m omega square r divided by root 3. So adding T1 and T2 would cancel out T2, and this 2 sine 2 would also be getting cancelled out. In the same way, we can write T2. T2 would be some m omega square r by root 3 minus mg. So this would be the value of T2. So how had we evaluate T2? From this expression T1 plus T2 is equal to 2 by root 3 m omega square r, we have subtracted equation number 1. So that gives us 2 by root 3 m omega square r minus 2 mg, and that would come out to be equal to 2 T2. And so dividing by 2 would give us m omega square r by root 3 minus mg, and the 2 in numerator denominator would cancel. So this would give us the value of T1 and T2. Now we have to find the value of omega for which the strings do not slack. So the string number 1 is never going to slack because both the terms in its equation are positive. Mg and m omega square r by root 3 both are positive. That's why T1 can never be a negative term. So only T2 can become negative or 0 term. So T2 has to be more than 0 at all times. So we can say that m omega square r by root 3. So this is for the part B. Part A we have already done. Minus mg should be more than 0 for the string not to slack. So it would give us m omega square r by root 3 should be greater than g. So this gives us omega should be greater than square root 3 g by r square root. So this should, for these values of omega more equal to and more than root 3 g by r square root, for these values of omega the string would not slack, especially the string number 2. So let us move on to our next question. So in our next question, we will be evaluating the case of a block which is resting on the inner surface of a cylinder. So you have a hollow cylinder, and on the inner surface of the cylinder we will be having a block, and that block is having some mass, and it would try to slide down. So how can we stop the mass from sliding down? So this is the mass n, it is resting on the inner surface of a cylinder. So how it is resting at all? It should slide down due to gravity, right? So the answer you will be getting, there should be some friction or some kind of force which should be helping the mass n stay up. But even friction is not enough without any normal reaction. So there should be some force, or we can say there should be requirement of some force which would keep this mass m sticking to the inner surface of the cylinder. So you can imagine a very good situation when we have a cylinder and there is some water in it, and you are making vortices inside the water, or vortices in the cylinder. So when vortices form, the water tends to stick out. The height of the water closer to the rims of the cylinder rises up, and there is a kind of deep point in the middle of the cylinder. So that means water tends to go outside. So in the same way, when we are spinning anything, things tend to go outside. In the same way, this mass m is trying to stick to the cylinder. It is trying to break open the walls of the cylinder and it's trying to stick to it. So we can understand this in a single, in one more way, which is the centrifugal force. So we can take a system in which we are rotating with the cylinder with the angular velocity omega, and there is centrifugal force acting on the cylinder m omega square r, and it is nullified with a normal reaction acting on the mass applied by the cylinder. So this mass m would try to slide down due to gravitational force mg, and there is a friction acting F which would prevent the cylinder from sliding down. So these are the forces acting on the cylinder. The question is, find the value of omega for which the cylinder does not slide down. So we have to find omega, right? Again we will be evaluating the limiting case. The value of friction goes to the maximum, and friction would be following the same rule which has been following, that is F is equal to mu n for maximum values. So friction would reach its maximum value mu n, and it would prevent the cylinder from mass from sliding down on the inner surface of the cylinder. So it's saying F is equal to mu n, and normal reaction n is equal to m omega square r. So we would say what is the value of friction? Friction is equal to mu times n. So friction would come out to be mu n omega square r. But this friction should be more than the value of gravitational force acting on the mass. That should be more than mg. So we can easily say that omega square r should be more than g by mu, or we can say omega should be more than g by r mu and square root. So this would be the values of omega for which the cylinder, the block, would not slide in the inner surface of the cylinder. So this is again one of those questions where we have to evaluate what are the forces acting in the cases of circular motion. So normal reaction, friction, gravitational force, what is going to happen? And what friction did is prevent the motion of the block. So it acted in a certain manner, and we apply centrifugal force. Again we can do the same question with the concept of centripetal force also. So let us move ahead. So now we will be taking a question of a slightly different topic, that is electrostatics. So that is one of the doubts asked in some group. So let us solve that particular question, which means that we are done with the chapter of circular motion and the force on it. So let us do that particular question. So the question is, we have a triangular rod, triangular system. And in that triangular system, some charge distribution is there, and we have to find the electric field due to that charge distribution in the plane of the triangle, and specifically at the centroid of the triangle. So pretty easy case. So let's see how we approach it. So we have a triangular prism, and we want to evaluate what is the electric field due to this charge distribution at the center of the triangle. So how do we do it? So first of all, we must know the expression of each triangle, each bar of the triangle at this particular distance or at any general distance. So let us derive the equation for that particular rod. So let us take a rod and let us take a symmetrical case. Or we can take an asymmetrical case too. So let us take an asymmetrical one. Let's say this is some dotted line on which the point at which electric field that is to be evaluated. Since we are talking about charge distribution, we are talking about electric field. So this is the point P. The point P is at a distance r from this charge rod lambda. So lambda is the uniform distribution that we have already taken. In the case of non-uniform distribution too, we can take this case and integrate in this way. So for lambda case, we have taken some distance x. Again, we will be taking some distance x, and from that distance, we will be writing the expression of our electric field. So at some distance x, we have taken some element dx. So in this dx element, what would be the charge present in the field? So charge present in this field, not field, in this element, the charge present in this element, would be lambda dx, that is charge charge on the rod per unit length multiplied by length. So charge per unit length into length would give us the charge in this particular small element. So the electric field due to this dx element would be in this direction. So that would be some field, let's say dE, and would be in radially outward direction. So we can take the component of this particular field in this direction. Let us take name that component dEp, and we have to eventually evaluate what would be the net electric field at point P. So what would be the value of dEp? The value of dEp, if I am taking one more symmetrical component over here and then saying that the field due to that component would also be like this, radially outward, and both these components would actually add up. So we are taking electric field due to two components, right? One this component, another this component. So due to these two components, we are taking the electric field, and their fields perpendicular to the rod is adding up. So we are writing the net dEp field not just because of dE, but because of both these components and the component and their electric fields adding up. Both these elements and their electric fields adding up. So this is dEp. So it's saying the electric field due to both these components would be Q, which is lambda dx, the distance between the element and the point, which is r. This distance is r plus r square plus x square, the distance squared. So that is square root r square plus x square. So it remains r square plus x square, and a cos theta component for this dE. The cos theta component would be some cos theta, and then taking 2 times because we are taking 2 elements. So this is the expression which we have to arrive at. So while arriving at this expression, we took some steps. First step was to identify the element due to which we are taking the field, and then writing the field. That would be the second step, that in which direction the field is going to be there. Then the third step would be identifying a partner element which sits directly opposite to it, so that we can try to find some kind of cancellation or adding up all the fields. For example, we immediately found that the component of the field dE in this direction would be adding up with a similar component. So I immediately took a symmetrical component. But we can do without a partner element too. And the fourth step comprised that we have to finally write the whole electric field by taking in consideration what is the net electric field at this point and what are the components that we are going to consider. So we are taking both the components, so we have added up and multiplied it with the 2 times sign. Again, there is one more component of the field which we have to think about. So that is this one. So as you can guess by now that the field due to dE in the horizontal direction or in the direction parallel to the rod would be cancelled out on both the sides, because these two components are equal, probably equal. But this won't be the case if this point P is not lying asymmetrical to the rod. Because it is lying symmetrical to the rod, that time we can say there would be always some pair of components for which the field would be cancelling out. But if there is no component of the field present in this direction, then there would be some d sin theta 2, and we can integrate that too also, and get some expression which is also easy to evaluate. But for us, these two components are getting cancelled out, so we are writing only dEp component, that is the vertical one. Now the question just remains that we have to integrate it. So integrating this expression, we get x, we can use x is some r tan theta. So we can see in this triangle, in this particular triangle, this distance is x, this distance is r, this angle is theta, which makes this angle also as theta. So x is equal to r tan theta dx is equal to r sec square theta d theta. because differentiating x with respect to theta. So tan theta differentiation is 6 square theta. And then we can say x square plus r square. That is adding these two values, x square plus r square, which is in the denominator. That should be simply r square 6 square theta. Since x is equal to r tan theta, this expression becomes r square tan square theta. This becomes r square 6 square theta. And again we can identify by even simplifying it even more. Substituting r square x square plus r square tan theta does the job. But as you can see, we are having dx upon r square plus x square over here, right? So we are already seeing the dx over here, x square plus r square over here, and we can divide these two. So dividing these two, we would get 1 upon r and only d theta, because 6 square theta would cancel out. So writing dep again, we can say this would be some t2k lambda dx upon this would simply be written as 1 upon r d theta, and we have cos theta remaining because it is already there. Now we will be integrating this expression from 0 to the angle which point P subtends at the end of the rod, since it is the symmetrical case. For asymmetrical case, we are taking the angle, this angle alpha and this angle beta. This angle would have been some alpha and this angle would have been some beta. So from minus beta to alpha, we would have to take the limits. And remember this point very clearly, that we have to take the angle minus beta, not plus beta. So we have to take the angle minus beta if beta is in this direction, minus beta to alpha. This would be our limits. Had we had taken the asymmetrical case, and even that case too, we would have to drop 2. Why would we have to drop 2? Because we have already taken the fields due to these two elements already. So we do not have to take the elements again in the limits 2 times. So since we have already taken 2 over here, we have added the fields due to these two elements, due to pairwise elements. That's why we will be only taking the elements due to one side of the charge. So one side of the charge, we will be taking the limits from 0 to some alpha. And if it were an asymmetrical case, we would have taken some limits alpha and beta. So be very careful with it. So from 0 to alpha, the electric field goes to some value EP. So integrating this value, we would get EP from 0 to EP, so 2k lambda by r, and integrating cos theta would give us sin theta, and the value goes from 0 to alpha. So this gives us the value 2k lambda by r is equal to sin alpha. So this is the electric field due to one particular charge at the centroid of the triangle. So what would be the net electric field due to all the 3 charges distribution, all the 3 rods at the center of the triangle? So that is what we have to evaluate. So that can be easily found, right? How? Using vector addition, we can say at the center of this centroid of this triangle, all these distances are equal. So since distance of the centroid of the triangle from all these rods are same, that means force exerted or electric field due to these rods at this point would be equal. So let us name this force due to only, or electric field due to one rod to be E, which is we have evaluated to be EP is equal to some 2k lambda sin alpha. So this is what we have already evaluated. Now we have to find the electric field due to all the 3 distributions. So how do we do it? So we have to find what are the directions of the field. So this electric field is in this direction. It would be coinciding with this vertex. This electric field would be coinciding with this vertex, like this. So what would be the angle between these two electric fields? So you guessed it right. The angle would be some 120 degree angle. And what would be this angle alpha? So if we were to calculate what would be the angle subtended by this point P by the ends, so this angle would come out to be some 60 degree, right? This angle would be some 60 degree because we are taking the angle alpha, which is the angle subtended by the point on the ends of the rod. So alpha would come out to be 60, and this is the value of EP to be some 2k lambda by r sin alpha, which is root 3 by 2. So this would come out to be some EP is equal to k lambda by r into root 3. So this would be the electric field due to one rod. So what would the electric field, net electric field due to this rod and this rod? So since the angle between these two electric fields is 120 degree, upon adding these two electric fields, we will get E only. So that is the point which we should be able to understand, right? When there are two vectors which are oriented at an angle of 120 degree with respect to each other, when we add them, we get the vector themselves. So in the same way, when we will be taking E here and E here, when they will both be adding, we will get the value E back to us. So the electric field due to this charge distribution would be E, due to this due to E, and adding up would be getting a single E only. So the net electric field at point at the centroid of this triangle would be E due to these two rods, and E due to this rod, and that would be in attractive direction. So it would be adding up with the electric field with the other fields. So this would, the net electric field would come out to be 2 times EP. So this would come out to be 2 times k lambda by r. Here the r is the distance of the point P from the midpoint of the rod. So the distance r is some L by 2 root 3. So substituting the value of r over here, so that would be L by 2 root 3 into root 3. So this is the expression for the net electric field at that point. So net electric field would come out to be some 4k lambda by L times 3. Because square root 3 would again go up, so it would multiply and get 3. So this would come out to be some 3 lambda upon pi epsilon naught L. So this is the expression for net electric field at the centroid of this charge distribution. So thank you for joining today and have a great day.